Good evening, all. Hopefully, y'all can hear me.
Yes, sir, we can hear you.
Super. Shall we get started?
Yes, sir, now we will be starting. Yeah. Mitara?
Ladies and gentlemen, a very good evening, and I would like to welcome you all for an insightful session on charging infrastructure innovations. I'm Mitara Pereira, your host for the day, and I warmly welcome you to the third workshop series of the Battery Technology and Charging Infrastructure for Electric Vehicles workshop series organized by IEEE Y2N Pro. To give a brief overview of this workshop series, this is a comprehensive course that offers both theoretical and practical insights into battery technologies and charging infrastructures of EVs. This series addresses the surging demand for expertise in the EV sector, focusing on battery systems and charging infrastructure. You will be able to explore the evolution, operational principles, and future advancements of EVs, delving into battery technologies and innovations aimed at enhancing efficiency and safety. Today's workshop focuses on charging infrastructure innovations too, specifically smart charging solutions, vehicle to grid, and vehicle to everything integration. Before moving on, we have some important announcements to make. We have already shared these guidelines to be followed during the workshop series. However, I will read the guidelines and make sure that you follow them for a smooth session. A quiz would be administered at the end of the workshop series on the 5th of October, where you will be assessed on the knowledge gain. The IEEE credential certificate will be awarded only if you achieve at least 80% on the above mentioned quiz and attend at least 80% of the session. Attendance will be marked at 3 given instances of the session. Therefore, please be present throughout the session. The recording of the webinar will be uploaded to the Google Classroom. Please rename yourself using the registration number provided in the handbook and your name if you haven't done so already. Today, we are honored to have a distinguished industry expert with us who will guide you through advanced charging infrastructure innovations, specifically smart charging solutions, vehicle to grid, and vehicle to everything integration. Thank you, sir, for accepting our invitation and joining us today to deliver the keynote speech. Dr. Beshan Kulapala is a distinguished tech entrepreneur and the Vice President of Technology and Innovation at Volt Charge in Saudi Arabia, as well as the CEO of Cyrus Sri Lanka. He co-founded Vega Innovations, where he played a pivotal role in developing South Asia's first electric supercar, unveiled at the Geneva International Motor Show in 2020. Dr. Kulapala also spearheaded the creation of ChargeNet, Sri Lanka's largest EV charging network, and AI Group, an agriculture technology solutions provider. Before this, he served as an engineering manager at Intel Corporation USA, where he led teams in developing integrated debug and survivability capabilities for CPU products and co-founded the Validation Core Unit. He holds a PhD in electrical engineering and an MBA from Arizona State University. Additionally, Dr. Kulapala serves as the chairman of the Sava Medical Clinic in Colombo and volunteers as a Scoutmaster, reflecting his dedication to both technological and innovation service. So, ladies and gentlemen, please welcome Dr. Beshan Kulapala to deliver the keynote speech on smart charging solutions, vehicle to grid, and vehicle to everything integration. The spotlight is yours, sir.
Thank you, Mitara. Thank you for that lovely introduction. Hello all. So today, hopefully, we'll cover some subjects that you all are interested in. Um, to be honest, I don't have a presentation per se because I wanted to go with the flow and see what gaps you all have in your understanding of charging technologies and how we can maybe find answers together on the open web so that I don't step on any NDAs or any agreements with the kind of the work that we're doing already. I hope that is okay. So hopefully this will just not be you listening to what I have to say, um, but you all also speak up as to how you understand of EV chargers. There were some sessions done before, and maybe you all have questions around it, so we can maybe try to catch up on those. And I must say, I have a team of engineers who develop EV chargers for our company. So it's not that I know all the answers. And I would also, go Google or watch YouTube video or read some document to know, more of it. So if you ask me a question, if I don't know about it, we can maybe go find the answers together. Yeah. All right. So that is the kind of the levels that I wanted to give. Now, let me ask you all this first. So there is AC and DC charging in EV chargers, right? So you all probably know the basics where the DC charger is the charging unit that takes AC voltage from the grid, converts it to DC, and then pumps it into the vehicle, into the battery pack. And then there is the AC version of it where one of the slow chargers or the smaller chargers would pump AC current and voltage into the vehicle, single phase or three phase. And the vehicle will have the onboard converter or the inverter to convert it from AC to DC and then, pump it into the battery. Right? Are we all clear on that? Is that something that we need to touch on to get the basics out of the way? Do you all understand the different standards and protocols used on these two methodologies? Anyone? If somebody doesn't know, maybe you can just send a comment on the chat. Again, this is not a not just me speaking to you all and then you all kind of listen and go away and whatever. Hopefully, we can have a more of a dialogue today. Anyone? There is 33 people on the call. If you all don't want to speak out, you all can send me a message. I don't see anything on the chat yet.
Excuse me, sir. I
Yeah.
think we didn't give them chance to unmute themselves. So, Hansi,
Oh, I
please.
see.
Yeah.
Sorry. Fine.
Provided.
Very good.
Yeah, they can unmute themselves. It's provided.
Yes, please.
This is given.
Hopefully, you all can unmute. I see some of you all are not on mute. So maybe. Are they able to unmute the organizers or are they restricted from speaking?
They are allowed, sir.
Sorry, you said yes, or will they be able to ask questions?
Yes, sir. They are allowed to unmute themselves.
Oh, they're allowed. Okay, very good. So, it's important that you all ask me the right questions so I can speak to the right problems. Or this would be very, very boring. I'll just, Google something and speak to you about it, and I don't think you all will learn much from that. So my question is, are you clear? Is someone not clear about AC and DC chargers? Or can we just skip that and go talk about something else? Because the basics are important, otherwise it's difficult to build on top of it. Right?
We do understand, sir.
Okay, very good. So if you all do, what are some of the protocols or the standards for AC charging?
Sometimes there are dual active bridges that convert the uh, voltage levels accordingly to the battery and the power supply.
Okay.
Specifically, I do not know the protocols.
Okay, very good. So then I think we should touch on it just so that we all level set, because EV charging is completely driven by standards. It's completely driven by worldwide standards. If you don't adhere to the standard, there is no way that you can either build a EV charger or charge a EV vehicle or any of that. So understanding what those standards are very, very important. Most of the early standards are freely available on the web. You can download it from various sites without paying for it. Of course, if you want to get the original, you'll have to pay for it too. So let me just take 10 minutes to go over the standards themselves. All right. Oh, sorry. Okay. I know the presentation that was done previously, talked about the PWM signal, the control pilot, and what that is. But I'll again go over it so that, if you all missed it, maybe that you all can, get up to speed on it. So, okay. So the first protocol is the IEC 61851. Right. So this is what we call the lower level communication protocol. Even the J1772 standard talks about the IEC 61851. So in the EV charging world, for the slow chargers, or what we call the AC chargers, so the charger connects with the vehicle, and there has to be a protocol in between for the charger and the vehicle to talk to each other, right? So in the early days, which is about 5 years ago, we had the 61851, where there is a single wire CP line, control pilot wire, that has a PWM signal. So it oscillates on a square wave. The duty of this wave varies. I'll tell you how. And the voltage of the signal also varies. Yeah. It would be good if I shared my screen. Hopefully, y'all can see my screen.
Yes, sir.
Okay. All right. So a good place to go is the vector.com. Vector has been in this protocol scene for EV chargers and other things for a long time. So they have some good information there. So this pulse width modulation signal, all of you all know what a PWM signal is, I hope. It's a square wave that goes, let's say to 0 to 1 or 0 to 5 volts or 12 volts or whatever in a square wave manner. So this CP signal can go from 12 to negative 12, right? So the voltage can vary from negative 12 to 0, to plus 12. So depending on the voltage level, the car and the vehicle will understand what state they are in. So there are roughly about 6 states. So if you are plus 12, there is no EV connected to the EVSC. This pulse width modulation signal is generated by the EVSC actually. So if the EVSC, the electric vehicle supply equipment, the charger, which is the EVSC, if it shows 12 volts, then that means there is no EV connected to the EVSC. Now, once somebody or the driver plugs the vehicle into the car, the PWM will immediately go to 9 volts. If you have a oscilloscope connected to this signal, or even if you have a like a multimeter connected, you can see this voltage drop. So if the EV is connected, it's going to go to 9 volts. And if the vehicle is also now ready for charging, it will change a resistor within the vehicle, and then the voltage will drop to 6 volts. And then when it's charging, the vehicle drops to 3 volts. And then if there's an error, it will drop to 0. And then if it's not available, then it drops to -12. So these are the kind of the states that this CP line communicates on. So the remarkable simplicity of this protocol with 61851-1 is that with the voltage, it shows what the state is. And with the duty of the PWM, it can show different information. So let's say, for example, if the duty is more than between 10% and 85%, then the available current is duty cycle times 0.6 amperes. So the important thing here is when an EV is connected to the AC charger, the EV can draw as much current as it wants, right? Because now it's trying to get AC voltage or AC current into the car. So so then you need to have a protocol to control the amount of current the car draws. Otherwise, you can flip the breaker in the house where the charger is connected, or even worse, you can burn the wires or some components inside. So what you need is to understand that the vehicle needs to tell, the charger needs to tell the vehicle what is the current that you can take out of my charger, right? So these are the different duty cycles that controls that. Now if most vehicles, I think maybe all of the vehicles currently can charge a vehicle or with a slow charger, AC charger, with just this CP line and the power wires going in. You don't need any other sort of a digital communication between the car and the charger for AC charging in this method with 61851. Is that clear? Because this is a Zoom meeting, it's very hard to know that if you all have picked it up, but I hope so. If you don't, please ask. So with this single wire, the car and the charger can communicate with this protocol, 61851. Yep. Okay. So now, when the charging world wanted to develop further, and the vehicles were getting more complicated and complex, and we wanted to get more features into this charging world, this single wire communication was not enough, right? Because this only has state and then the duty, which shows the amount of current, right? If you want to do vehicle to grid charging, for example, you have to send a lot more information into the car to make sure that it understands how to give current or voltage out into the world. So what they did was they made the duty cycle, if it's between 3% and 7%, then it forced the vehicle and then it forced the charger, if it's available, to go into a higher level communication protocol called ISO 15118. There's a DIN number, but don't worry about that. So the next important one after 618-61851-1 is this protocol called ISO 15118. So that is how this charging systems has evolved. Because these are standard protocols, the charger is standard, the vehicle is standard. Without understanding the standard itself, there is very little knowledge that you can speak of EV charging. Well, there is some in the power electronics side. I think this is what one of the students just mentioned, that you can have different bridges and different topologies for AC to DC conversion. But that is in the power electronics domain. But for the charging domain, you need to understand these two protocols on a minimum, right? So this is a learning from my last 10 years in the e-mobility side, that these standards are what you need to start from, right? So this is if you hopefully you all will appreciate that this is one of the key things for understanding EV charging. All right. So another good, I can share these links with you all. These are all Google, so there is no problem of sharing these. So you all have these and you can read offline. All right, so I sent you both. So on this ISO 15118-2 is the actual digital communication between the vehicle and the charger for AC charging as well as for DC charging. So both typically uses the same protocol. Now the vehicle to X, which is what we'll be speaking about in a little bit, the vehicle to everything, also builds on this top of this protocol itself, the 15118-2. So this is an important standard to understand. I think if you're accessing the standards through your university libraries, I think you can get the standard for free, which is a very, very valuable thing. You should do that immediately if you have access. Or sometimes if you search for the Indian version of the standard, the Indian government has changed this standard slightly and then released that standard as a free document. So you can legally download the entire document for free with very little changes in the standard. So that is a awesome way of getting this standard for free also. Otherwise, this will cost you about $350 or something to download, which I think is a lot of money. Anyways, so this 15118-2 specifies the digital communication between the electric vehicle and the charging equipment, right? So in a digital communication method, what are the sorts of systems that you're already aware of? Can somebody answer that for digital communications? What are the protocols or architectures that are out there? Anyone? No? Some of y'all have already graduated, I think, and should be using some of these. I think any project you would use. Don't feel shy. CAN, very good. Okay, so there is CAN. There is serial communication like the RxTX, which is one of the easiest ones. There's I2C, SPI, RS485, RS285, all of these other, protocols as well. So normally they would use two wires, as well, some are single wires, some uses 6 or 7 wires, some 8. But in this instance, ISO 158-2, the digital communication happens through the CP line also, but using PLC, right? Now, if somebody is not, this is not the programmable logic that I'm talking about. I'm talking about power line communication. So what happens in power line communication is the wire that takes the current or the voltage, the signal is modulated on top of it. Right? So it's like this. The sine wave travels on the AC line, and then you modulate your data into the wave itself. So if you have a square wave, then you can modulate it differently. If you do 151.8-2, then I hope there's a picture. So in this instance, on the square wave itself, this PWM wave that we talked about for the previous protocol on the CP line, on the charging pilot signal, you modulate your digital data on top of it. That is how ISO 15118-2 communication happens. Yeah, hopefully everybody is still with me. If not, send me a message. Okay. So now you have this new method where the previous charging connector is still the same. The number of wires are the same. And there is backward compatibility to 618-618.1. But now you can have more features on this for a newer advanced charge. Right? So this is what you call smart charge, where you have this digital communication on top of your previous charging system. And the digital communication is 15118-2. Good. All right. So with smart charging, there is a lot more now you can do, because now you have a different way of talking to the vehicle. You can set all sorts of messages. You can do authentication. You can do security checks. You can, tell the, car can give you information about its problems. The charger can give the car about its problems and all of that. So in this method, there is this set of data that the vehicle and the vehicle and the car can exchange various parameters and details. So there is a way, for example, the car will hold the security or the authentication username and password, for example, to charge. So normally in a basic charger, you have to go to the charger and tap a RFID card or use your app to charge and things like that to tell the charging system who you are. But with smart charging, now you could have the certificate or a authenticated piece of code stored in the car. So all you have to do is plug the vehicle into the charger, and then smart charging will exchange the certificates that are installed, and the charger will know who this person is to get the money for charging. So you'll see these certificate installations, updates, and things like that. Even the payment details can be sent through. So there's a lot more information here. The spec or that standard is quite large, so there's no time to get through the entire thing. But if you go down this document, you will get to vehicle to grid charging. This is where the charger and the vehicle will discuss how to pump energy out of the car into the grid. So this we do, hundreds of times through the solar inverters, right? If you have a grid connected solar inverter, the energy that the solar panels create gets through the inverter. It converts from DC to AC. It has to match the sine wave of the grid. It has to match the frequency. Any restrictions with the power of the thing. So it has to be either real power or the various other phases and things that have to match, so that the grid, the inverter can pump the energy out into the grid. So if anybody has grid tied inverter solar, I'm sure the university has, or if anybody has at home, then that is how it works. So this is a fairly straightforward thing. But when you set up your solar inverter, you have to tell what are the restrictions of doing this in your local government or with CEB or LECO or in Sri Lanka. So if a solar inverter installs a grid-tied inverter, they will tell the inverter through the settings what is the maximum frequency that you can go to? What is the minimum frequency that you can go to? What is the maximum voltage or the minimum voltage that you can operate in? Things like that. So this has to be the same for a EV vehicle pumping energy out of the car into the grid, right? Because if the car doesn't know at what frequency what maximum frequency that it should use for your particular country, then there is a problem. Then LECO or CEB won't allow you to pump energy from your car into the grid, right? So we need to be very careful about how that is handled. So that is why there is this protocol of exchanging so much information back and forth as to how this should happen. So I'll show you another diagram. So this switch vehicle to grid, I found this to have a lot of good information. So this website has a little bit more information about what those messages are. So there is the energy transfer mode, right? So energy transfer mode will then have energy transfer mode type, and then the energy request, the maximum energy request, the minimum energy request. Then it can have details like the maximum charge power, maximum charge current, minimum charge current, maximum voltage. And then if it's discharging into the grid, what is the maximum discharge power, minimum discharge power, maximum discharge current, and the minimum discharge current, things like that. And if you read more, it will talk about the frequency and other information that you need to set. So this is part of this vehicle to grid piece of how the charger and the vehicle will talk to each other to make sure that that this is done properly, right? So there is battery power, there's energy stored in the EV charge, in the EV vehicle, in the battery. There is an onboard charger that is in the you look at the components. Let's talk about this one. So there is the high voltage battery inside the vehicle. There is an onboard charger, and then this is of course for a fast charger, but for a slow charger also, it's a similar, where the onboard charger is inside the vehicle itself that will convert the DC into AC and push it back out into the grid. So again, that the power electronics of that piece is this bidirectional onboard charger that you have. So if you want to look at a picture of a so it would pretty much look like a component like this. It will be installed inside the vehicle. It's bidirectional, meaning AC voltage can come from outside, convert to DC, and then plug into their battery. Or the battery current can come into the bidirectional EV charger from the other direction, converts to AC like a solar inverter, and then plugs, pumps it back into the grid. So, pretty basic. And then the power electronics of these bidirectional EV chargers can have various different algorithms and architectures. It could be a boost buck kind of setup, or various different things using various different semiconductors as well. So it could be MOSFET or GaN technology, or CMOS, or things like that. So I wouldn't get into too much of the power electronics side of things, but this is how the protocol works, right? Okay. So that is on the AC side of things for vehicle to grid. Now the same thing with the DC side as well. With the DC world, we saw a picture before. Let me try to see if I can get that again. On the DC side, voltage from the grid AC is converted into DC on the charger itself outside of the car, and then the DC power is fed into the vehicle. So this has two protocols, CHAdeMO and CCS2. If you didn't catch this on the last maybe training, there's multiple different connectors for DC. This is the type CCS2 or CCS type 2 connector. This is now the universal connector for most vehicles, I think. Then the older Japanese versions, like the Nissan Leaf and some newer Japanese cars also for the Japanese market, has this CHAdeMO protocol. So CHAdeMO has a different protocol that uses CAN bus for communication, whereas CCS2 uses the ISO 15118-2 PLC, power line communication for communication. So these are way two different protocols, but it's for DC charging, for the vehicle and the charger to talk together. Yeah. All right. So even in the DC world, the vehicle to grid is still pretty much the same. The charger will tell the vehicle, what are the restrictions in this country for vehicle to grid charging. The vehicle will tell the charger what are my restrictions, how much power do I have, what is my maximum current I can give, and so on. And then when they agree on each other with their parameters, they will start pumping energy out and ensure that the compliance is met for vehicle safety as well as for the grid safety. So that concludes my part on the vehicle to grid. And then maybe hopefully all had a quick summary about the charging worlds also. Any questions on this part before I go to vehicle to X? Y'all can type it in the chat, please, if you do. If there's anything that I wasn't clear, or maybe I should have done a better job in explaining. I'll give a few minutes for some people to type it in if needed. Nobody? All right. So quick summary again, AC charging and DC charging. AC charging had 61851 previously, just basic CP line communication about 5-6 years ago, or maybe more. And then they wanted to make it better, and then they put ISO 15118-2 on top of it, which has the digital communication part that can then talk to the vehicle and do vehicle to grid and all sorts of other smart charging work. And then on the DC side, there is CHAdeMO and then CCS2. CCS2 is very similar to ISO 15118, almost the same. And CHAdeMO is a little bit more different, right? Okay, so one more quick thing. So BYD vehicles have a vehicle to grid unit. They call it load adapter. So there has this nifty cable, a vehicle to load option. No, I forgot the name. Well, it's this little adapter that they have. I think it's this one. Yeah, there you go. One side has the connector, and then other side has these multi connector that we have, so that you can plug any 13 ampere plug. So this connector has inbuilt microcontroller that will tell the vehicle that to go into a vehicle to grid mode, and to support roughly about 3 times of 13 amperes to support the charging. Yeah. So, I think other vehicle manufacturers will also have these type of little nifty things for people to use. So if you go on a trip somewhere and you want to plug in your speaker, then you can just use this. So a few questions on the charging side. One is on the bidirectional inverter and the bidirectional charging. So again, there's various different topologies for bidirectional charging. This is one of those. So this has 2 stages, microcontroller driven. So the first stage has a DC-DC converter and the second stage has a DC-AC converter. So what happens here is that battery voltage or the solar voltage comes in here. You raise it or you lower it to a voltage that you want to operate on. So let's say your battery voltage is 800 volts at this point, but your inverter, you want to operate it at 400 volts. That is what your system is set up for, or your PCB or your components. Then you do a DC to DC buck at that point to reduce the voltage. So your current will increase. And then at 400 volts, you will do 400 to AC. So you have an inverter here that will convert it to AC. You match the sine wave and then the other frequencies and whatnot to match the grid voltage, and then you pump it out. So this is a pretty much a standard bidirectional charger. It's bidirectional because energy can flow this way from DC to AC. Or if you put AC voltage first and then you convert it to DC 400 and then 400 to 800, then it can go the other direction also. So that is what you call a bidirectional charge. Wireless charging. I have very little knowledge on wireless charging at the moment because it wasn't part of the session today. So maybe we come to that afterwards if there is time. What are the countries that accept V2G? I think a lot of countries do. I don't typically know there is any restriction, or even if a country can really restrict because the vehicle comes with that feature, and if you have the converter, then you can plug it in. So they would have to limit or restrict the charger or the converting device, which I think again is maybe a little bit difficult. So at the moment, I don't think it's restricted per se. I might be wrong. All right, so let's move to the next piece of thing, the vehicle to X. All right, so vehicle to X is a totally different concept from charging, and I think I'm hopefully talking about the right V2X. So with the advance of technology and with 5G connectivity in particular, the amount of data that you can pump into a mobile vehicle or a mobile person to a cell phone or other things, a mobile phone is pretty much endless, right? There's so much bandwidth that will be available with 5G if it's done properly. Now with that amount of energy, that amount of data rates, you can do a lot more technological innovations around your mobility. So it doesn't have to be electric vehicles only, it can be other vehicles also. So the need for the longest time, I think for the last 10, 15 years, people have been talking about how vehicles can talk to the traffic lights or the street lamps, or the vehicles or the ambulance can talk to the vehicle, so that when the ambulance comes, the vehicle knows that, an emergency vehicle is coming, that you need to make some space and things like that. Or if there's an accident in front in a highway, then vehicles can communicate and tell vehicles in the back that there's accident and you need to slow down immediately so that you don't have a pile up or you don't have many vehicles hitting the single accident. So things like that can be done with vehicle to vehicle communication or vehicle to X, right? So this talks about how communication is done from for vehicles to any other device out there in the world. So early on, there were two protocols in this front. One is called C-V2X, which means cellular to vehicle to X, or the other one was DSRC. DSRC was it is for dedicated short range communication. So there were two of these protocols or standards that the world was seeing for the longest time. But recently, in a US court ruling, they ruled that the V2X is the right or the preferred protocol in the US. So there is certain restrictions for the DSRC. So a lot of people will now, I think it's safe to think that this T-V2X will take precedence, and a lot of technologies will be developed on this. And this is a good thing. We don't want to have two different kind of technologies and then having to deal with all sorts of the practical implications of having two different standards. Right. So I will share you this Altium document. I think has a lot of good information. So what is this C-V2X, right? So if you take the spectrum of the frequency spectrum, C2X is somewhere here. DSRC was somewhere here, and then your Wi-Fi connectivity was around here, right? So this is around 5.9 gigahertz is the frequency that C-V2X was operating in. So what does this mean? So it really means is that like you have a Wi-Fi router at your house, there is now a different router that is designed to communicate between vehicles and between vehicle to other things that you fit into the vehicle. And then a similar router will have to be on the other end on a traffic light or whatever it is, right? So if you want to look at, what are the routers out there, I don't think this is called a router, but the hardware part of it. So there's few companies that are having these at the moment. It's not widely enabled in the markets yet because this is still new, but a development board would look like this. It's the V2X. So it uses that frequency range to digitally communicate between various other devices. So if you dig in further, so that device, if you look at a development board from STI, maybe I should. I'll share this link here. So if you want to buy a development board for your project or something, it could be something similar. So it's just another development board, right? You don't need to scratch your head as to what's going on here. You have a microcontroller or a processor. There is memory and there is eMMC for storage and things like that. Pretty standard. Then it has these automotive features. It has a crash detection accelerometer, right? If there's a crash, it would detect that. It has GPS, or what you call GNSS now, which is better than GPS, I think. Then it has a 6-axis accelerometer, odometer, and various things to measure the movement of the device or the car. Then it would have the standard Ethernet port, the USB ports, the reset buttons, the backup battery, CAN bus, things like that, which you have on the Raspberry Pi even. JTAG connector, SD card, these are pretty, common ones. Then you would have the LTE modem, which is the this is the cellular modem for low bandwidth data. Then you have Wi-Fi. So if you want to have your mobile phone connected to this device, it has Wi-Fi. Then it has the V2X module, which is the thing that we talked about, the C-V2X module. Then various other sensors. So the applications are mostly for automotive and smart antennas. So if you have a smart traffic light, it would have a smart antenna with this. Then precise positioning and so on. So a device like this would have a block diagram of like this, where you have the microcontroller with the memory, you have the different Wi-Fi and other connectivity, Bluetooth and things like that. You will always have a power regulating system. You have the V2X now, then the GPS part, accelerometer, precision GPS, then other sorts of different connectivity for data for the other systems in the vehicle. So using a system like this, if you have it on the vehicle and then you have it in the traffic light or at the police car, ambulance, then you can have various different applications that you would write on top of this for usage. So there will be a huge industry now that will start or have already started that will create this kind of smartness between the vehicle and the other devices around, and vehicle to vehicle as well. Because electric vehicles are inherently a complete electronic system and has so many microcontrollers, so many computing powers. Electric vehicles have added advantage on this vehicle to X, because then you can limit the speed or the power or the torque. You can do automated braking, for example, if you want to have that kind of features. If there's a red light and if somebody's coming really, really fast, can you use technology and stop this car? So things like that can be taken into account. So this is the vehicle to X part of it. This is still a very new industry from what my small research had shown me. I haven't done anything on V2X yet, but it seems very interesting. And that this might be a good area also to look at. So that is my story on the vehicle to X part. And if you look at DigiKey or other devices, there is a lot of other information on various different V2X systems that are out there, like a smart tag, for example, that can be on the windscreen. So you can track vehicles going through the highway exit. You can automate payments, things like that. If somebody crosses a red light in a traffic light, then that person can be tracked immediately. There's a Wikipedia page on V2X, so that should give you some information. It has some good links also to get you to understand more about V2X. Yeah. So that's my V2X part. It is a little brief because, to be honest, I haven't done anything on this. And there's not a lot of information on V2X as well, just like EV chargers. And I think 10 years ago, when you wanted to research on EV chargers, it was very similar to trying to do research on V2X. Not a lot of information, not a lot of content, PDFs, YouTube videos, and things like that. But now it's everywhere, right? EV chargers have become more like building a desktop PC. You buy different pieces and you put it together and you have a computer. So similarly, the industry has moved into this modularization in the vehicle EV chargers also. Without doing a lot of work, you can put a charger together by buying components and plugging it together and doing a lot of testing. So the industry has made it very easy to get into these technologies. So it will be the same for V2X as well. Yep. Any questions on this section? All right. If there isn't, are there any questions on on EV charging as a whole, like in car technologies or the charger? Anything that I didn't talk about today? Maybe you all heard about it in a previous discussion, but didn't really wanted more information about it. Anything on EV chargers that you want to ask before we conclude? I think the organizers had kept about 30 minutes for questions. Anyone? No questions? What is the most suitable EV charger for Sri Lanka? Okay. So interesting question. Actually, good one. For homes, it's mostly AC chargers because there is really no point doing DC conversion and charging at homes with DC. Homes have restrictions in Sri Lanka in terms of power. Most homes have about 6 kilowatt or so of power available for single phase. So if you put a 7 kilowatt charger in a house with a 6 kilowatt availability, your breaker at the meter will most probably go off, or you won't have enough power at your house for other things. So you need to charge at a lower rate. If you have three phase, of course, you can go up to 11 kilowatt pretty easily. There's enough power available. But some cars and chargers operate at 22 kilowatt, and I don't think domestic lines can go up to 20 kilowatt, if I'm not mistaken. Check on that. So what we suggest is to charge at 11 kilowatt most of the time. So I think some places have 22, but not everybody. So for homes, it's AC charging. For offices, for places where people would park for 4 hours or more, then again, those are also AC chargers. So parking lots, your office, your office spaces and things like that will be AC charges also. But anywhere that you want to charge very quickly when you're going on a trip or when you're at a shopping mall or at a grocery store, for example, you would want to do DC charging to quickly charge. Simply because the battery pack is getting much bigger in vehicles, so you need to have a lot more energy pumped in. The BYD vehicles currently has about 44 kilowatt hours standard. Some can go up to 60 or even 80 kilowatt hours. So for those locations, what we recommend is the DC charging. We are installing DC chargers with the Keel supermarkets now. So pretty soon there'll be a pretty good network of EV chargers for fast chargers or DC chargers for your usage. DC chargers most typically have three phase and needs power from like 30 kilowatt onwards. And some chargers can go all the way up to 1 megawatt. So the power is limitless. Some big vehicles like the prime movers, container movers, or electric buses and trucks, they can charge with two connectors plugged at once. So they can easily charge at 150 or 250 kilowatt at power ranges. So how do you power these kind of chargers and how do you keep the grid safe is also a big area that people need to work on. Yeah, good question. Any other questions? No? So important thing to understand as all Sri Lankan locals here on this group, I think, through Vega and ChargeNet, I have been in the EV charging business for the last 11 or 12 years now. And we developed everything with Sri Lankan talent and resources and expertise. And now we are doing this again in a company called Cyrus EV Chargers, and we have a brand called Volt Charge, that we develop various different EV chargers. So this is an area that you all can also get into and develop services and products. You'll be our competitor, but we like competitors, and we want to have more people get in on this, right? So it helps the ecosystem here. It helps to have a trained team of uh, expertise in the country so that we can do bigger and better things. So hopefully people will start looking at this. Vehicle to X is new, so I think that's a very good place to be in at the moment, because you might have some cutting edge idea or technology that you could develop before the other guys. But all of these are in this e-mobility kind of technology sphere, and I think those have going to grow by billions and billions of dollars. So I think it's a good area for everybody to understand more and be. So that is my talk for the day. If you need to ask me anything offline, you can reach me on my LinkedIn page or on my social medias. LinkedIn is preferred. What's the idea? There's another question, sorry. What's the idea regarding commercial EV for local market? So I know the ports are looking at electric mobility because it helps bring their costs down and to have a more greener kind of fleet. Electric buses are great for advanced countries that has a lot of money, but because the buses are so expensive, I don't really, personally, I don't think it's Sri Lanka can afford to buy EV buses and put it out in the road. We can buy maybe 10 or 15 diesel buses for that same price. I'm not talking about Tata but diesel buses, but the better ones that has the lower uh, chassis for loading and unloading. So I don't think we are ready for electric buses in terms of our problems that we have with economy, but to have a good transportation system, I think it's better to look at diesel first and then get into electric buses. But for the cars and the other vehicles, I'm totally convinced that electric is the right way. Good. I think that's it for me. So thank you very much. One more question. What are the experiences about safety? So there is a study that was done, and I think one of the insurance, insurance companies had a big event recently at Shangri-La, and the keynote speaker from Singapore mentioned that there is no scientific evidence. There's no scientific evidence that electric vehicles are more dangerous than petrol vehicles. So I think all of these fires and things like that, you hear about it in the news just because it makes good news. But there's equivalently amount of vehicle fires for petrol cars and things like that. So in terms of safety, I think still there's a lot that needs to be done, but I think there is no inherent problem. The new battery systems are designed in such a way that has internal fuses to go off if there is a shortage and things like that. So I think safety wise, I don't see it a big problem. So EV charging and DC EV battery and DC charging is a common question. The manufacturers also don't have any restrictions on DC charging of EVs. So we don't see that anymore. Of course, common sense is to charge slowly most of the time. So use the AC charger as much as possible at home and things like that. But if you need to go on a trip or you need to pick the charge, there's no point plugging and waiting for 2, 3, or 4 hours. Then you have to charge with DC, and that's okay. And these batteries are designed that way. And BYD vehicles, for example, has an 8-year warranty on the battery. So I think there's nothing to worry about in terms of using DC chargers. V2X in Sri Lanka. I think this would not be enabled yet. If you want to get a V2X modem into the country, you probably have to go to TRC and explain a lot of things to get it cleared. You all know how fun that is. So at the moment, I don't think there's any work that is being done in V2X in the country. I might be mistaken. I don't know what everybody does, but I'm just guessing. But you can do interesting business models, like if you want to track a fleet of lorries, you could probably use V2X to do that, depending on the cost and features that you want. So there might be business opportunities, but I think V2X, the primary opportunity would be to develop technology for other advanced. When I say advanced, I mean countries that uses V2X right now rather than the local market. But there might be business opportunities here. Good. All right. Thank you very much, guys. Hope you all had a good session, and hope you all have complete this entire course. And good luck to all of you all.
Thank you, Dr. Beshan, for that very informative session. Your insights have truly added depth to our participants' understanding of smart charging solutions, particularly V2G and V2X integration. Your ability to simplify complex concepts is commendable. I believe the foundation you have laid today will surely help our participants in their academic or professional journey. Now I invite the audience to raise any more questions or doubts you may have about the content that was discussed today. I encourage all the participants to make the maximum out of this opportunity and ask questions and clarify doubts.
I think a number of good questions were asked. If there is any offline questions, you can reach me, however, and I'll be happy to talk to you all more.
Right, time is of value, so we will head on with the program since there are no more questions raised. However, if there are any problems arise, please reach out to the Y2NPro team and we will do our best to get the questions answered. Moving on, we would like to take a moment to express our gratitude to our esteemed speaker, Dr. Beshan Kulapala, for accepting our invitation and sharing his valuable knowledge and expertise with us. Please accept our token of appreciation. Your presence here has set a high standard for the caliber of learning we can expect from this workshop series. Thank you once again, sir.
You're very welcome. Thank you for having me. I had a wonderful time. So, thanks.
Thank you, sir. Before proceeding, let's take a group photo to remember this valuable time we spent today. I kindly request the audience and the OC members to switch on your cameras to take a group photo. Let's wait for another few seconds till everyone is ready.
Excuse me, I can't open access to video. It's telling the host has stopped it.
Yes, we will work on it, Hansi.
Permission is given to start videos. Can you recheck? Is it still not working for you?
Okay, I think we are good to go now. Everyone, get ready, and on the count of 3, I'll give you a cue to smile and pose. 3, 2, 1, say cheese. Okay, are we good to go, Hansi?
Yeah, shall we take one more?
Yeah, sure. I'll give the count and let's smile. 1, 2, 3, say cheese.
All right, Nitara.
Okay, thank you all.
Please share the picture with me also, please. Thank you.
Yes, sir, will do. Also, please note that the quiz will be conducted on the 5th of October at the end of the workshop series. We have now shared a feedback form in the Zoom chat. Also, you can scan the QR code on the screen to access the feedback form. We kindly request you to take a few minutes to fill it out. Your feedback is extremely important to us, as it helps us to continuously improve and provide you with better experiences in the future. This will also be considered for your attendance. Moving on, the next session will be held on the 31st of August from 6 p.m. onwards, where Professor Anurag Vijayapala, Head of Department of Electrical Engineering of University of Moratuwa, will join us to take you through energy storage integration. As we now have reached the end of the session, we sincerely hope that you found the workshop informative and thought-provoking, and that you leave with new insights and ideas. And with that, we conclude today's workshop. Thank you once again, and have a very good night.
Good evening, sir. Can you hear me?